electromagnetic wave. So, and as you know that an electric field and a magnetic field, they may or may not require a medium to propagate. So it's a property of the electric wave as well as the property of the magnetic wave. So therefore, we can see the electromagnetic radiation that, travel space, okay, or universe. So therefore, since the light comprises electric and magnetic field, and it's the properties of the electric and magnetic fields that they do not require an underlying medium to travel. So therefore, light wave may or may not require an underlying medium to travel. Is it clear?
Yes, sir.
So now the question is how this, as you know, the wave, it travels from one person to another person. The question is how this light travel. We can also visualize that light can one point to another point. For example, we know that the light comes from our sun. It normally it roughly takes 8 minutes to reach on Earth's surface. So we know that light can travel from one point to another point. So but the question is how this electric and magnetic field they travel. So in fact, the electric and magnetic field they oscillates. We have already studied great detail about great detail about
Sir, you are not audible.
Hello, sir.
Sir, you are not audible.
I think sir is disconnected.
Yes, sir. Technical issue.
hello. Hello.
Yes,
Yes,
sir.
sir.
Yes, sir. Sir,
Okay. I'm sorry. Suddenly, the power gone out. So therefore, I
sir, you're not audible. Yes, sir.
Hello.
Yes, sir.
Okay. So am I audible?
Yes,
Yes,
sir. Yes.
sir. Yes.
Okay.
Yes, sir.
Please let me know when I get disconnect. Okay. Please let me know over WhatsApp. So how these electric and magnetic field they oscillate when light wave travel. In fact, they oscillate in a such way that the
Sir, the
oscillation.
screen is not visible.
Okay, just a moment.
Yes, sir.
Is it visible now?
Yes, sir.
Yes, sir.
Yes, sir.
So everybody understood, right? That when light wave travels from one point to another point or one space to another, one position to another position. In fact, the electric and magnetic field they propagate or they oscillates along their directions, and the oscillation direction must be perpendicular to each other, and they must also perpendicular to the propagation direction. That means the direction at which the light or the electromagnetic wave they propagates. So this has been shown by this schematic diagram, and you can see that this magenta color it represents the electric field oscillation directions or propagations. You can see it propagates along x-axis, whereas this cyan color, which or you can see the sky color, it represents the magnetic field oscillation direction. Okay, and you can see both of them, the oscillation direction is perpendicular to each other, and they are also perpendicular to the propagation direction. And this condition is known as mutual orthogonality relation. That means where the E cap is the unit vector associated with the electric field, B cap is the unit vector associated with the magnetic field, and K cap is the unit vector associated with the propagation direction, or we can say the wave vector direction, which is represent K cap, K vector. That will also study in great detail as you progress. So do remember, so this satisfies the vector curl rule, or the cross product vector rules, E cap, B cap, right? You can do, and if you can the right hand rules, thumb rules, then it will come out that will indicate the propagation directions. That therefore, so this schematic diagram is consistent this mutual orthogonality relation. And if I say, if I flip the electric and magnetic field direction, so if I say no, so this represent the electric field direction and this represent the magnetic field directions. So what would be the propagation direction? This will be inside the plane of paper, because you have to E cross K, it will go inside. So therefore the propagation of the electromagnetic wave will be inside the plane of paper rather than coming out the plane of paper. Everybody knows from the cross product rules. Okay, and as we know that it is the nature of both electric and magnetic field that they do not require an underlying medium to travel or propagate. Therefore, light wave might not require a medium to travel. And then, as you know, that there are two different type of waves possible. One is transverse wave, another is longitudinal wave. By the way, you can hear me, right? Am I audible?
Yes, sir.
Yes, sir.
So
Yes,
here
sir.
is here is a little bit about wave, and as per the definition, that anything which varies periodically in both space and time is known as wave. So if you remember the oscillation chapter, before we formulate a statement, we looked at group of examples, and then we analyze them. Then we develop a statement about oscillation. Similarly, then how we can develop these statements, which I have written down here. So anything varies periodically, both space and time is known as wave. What does it mean? And everybody knows about the water wave in let's say water reservoir, let's say water pond. So how water wave travels? You throw a stone, or disturb, let's say, the center of the water reservoir, let's say pond, constantly, right? You can make disturbances, and what will happen? The waves, it will travel away from the disturbance point. And since we are applying at a point, so the wave will travel in circular fashion to the bank of the water reservoir. And for a given instant of time, if you look throughout the water reservoir, what we'll find that the water variation will be like this. So let's say this is the center of the water reservoir. What we'll find that the water variation from the center, it will be like this in all directions, right? So it means that you can see the periodic oscillations of water levels at a given instant of time. So therefore we can say it oscillates periodic over space for a given time. Okay, and if you focus on a particular portion, let's say this portion of the water reservoir, so what will happen? And in this position, if you look if you observe for a given time, right? So what we'll find? So in this portion, what we'll find that the height of the water level will also fluctuate in oscillation manner for a given portion or point. And if you look over time, so it will also oscillate. So now you understand that when we talk about wave, it not only oscillates periodically over space, but also periodically over time. Okay. And then you may ask question, can we, take this in a separate, the space oscillation and time oscillation? No, because it is associated with the wave. So therefore we cannot make them separate. They must be coupled. So therefore the statement, as I given the example, the water wave in water reservoir. So you can develop the statement for the wave. Anything which varies periodically in both space and time is known as wave. Is this clear to everybody? What I wanted to tell you or convince you? Yes or no?
Yes, sir.
Yes, sir.
So now
Yes, sir.
and there are, as you know, two different class of waves. One is longitudinal wave, and the second one is a transverse wave. So what are they? In transverse wave, you can see, so this is the propagation direction. That means it travels from left to right. If you consider it's a one-dimensional wave for the simplicity. So what will happen? So here the particle associated with the wave, or the medium associated with the wave, they do oscillate perpendicular to the propagation directions. Here you can see these arrows represents the oscillation direction, and it is perpendicular to the propagation direction. Then it's called transverse. Transverse means perpendicular, so therefore it's called transverse wave. And classic example of transverse wave is the water wave in a water reservoir. And there are other group of waves, for example, sound wave. What will happen? The particles or the mediums, the particles of the medium through which the sound wave travels, what they will do? They oscillate along the propagation directions. Okay, so you can see along the propagation direction. So therefore, it's a longitudinal wave. And you may ask question, when a wave travel from one end to another end, so the medium is associated with it, and therefore particles are also involved in the in this wave propagation. Okay, do this particle, propagate from or move from one point to another point or one end to another end? No. So in fact, the particle of the medium, they do not leave their mean position. They oscillates around their mean position, either perpendicular to the propagation direction or along the propagation direction, as you can see here. So these particles do oscillate around their mean position, and here also up and down around their mean position. This transverse wave in terms of crest and troughs. So the thing is that the particle as associate the medium, they do not travel from one end to another end as wave propagates, but the energy that transfer from one particle to the another particle or group of particle to another particle. So therefore, the wave carries energy as it propagates. So is it clear to everybody? Am I audible?
Yes, sir.
Yes,
Yes.
sir.
Yes, sir.
Is it clear? So if the question will come, when wave travel from one end to another end, do particles, also move from one end to another end? No. Actually, transports from one end to another end. For example, this particle will collide with the nearest particle and it will transfer the momentum energy. It can gain and it can also transfer, unlike this. Okay. So now, so this is, little bit about wave. And if I ask you question, light, which is, electromagnetic wave. So this is which kind of wave? Is it longitudinal or transverse? Immediately you can say it is a transverse wave, because here the electric and magnetic field, they do oscillate perpendicular to the propagation direction. So therefore, light wave is a classic example or well-known example of transverse wave. So now, at end, we know that light comprises electric field, magnetic field, and therefore it might not require an underlying medium to travel, and it is a transverse wave. So these are, some qualitative things, but to solve a problem, we need expressions. Then how we can develop mathematical expression or mathematical statements to explain the wave. For example, in oscillation chapter, we got equation of motion in terms of differential equation. Then we solve it. We got displacement, velocity, acceleration, and therefore energy. So similarly, can we develop a mathematical statements to represent wave? Yes. So how will it develop? As you know that anything that varies periodically over space and time is known as wave, and therefore we can, develop a mathematical statement as follows. Okay. So, so if you remember, when we solve, oscillation chapter, we got that the displacement, which is a solution, this is A sine omega t plus theta. We derived, explicitly from by balancing the force equations. In the same, similar fashion, not the exact way, but the similar fashion, you can derive the solution, the psi rt, right? And what would be the solution? Since it is oscillating both space and time, then you can write A sine k dot r minus omega t, right? And we know sine omega t, here sine omega t, and k is the wave number and r is the position vector, and this is the dot product, and phi is the phase factor, right? So you can split it, you can write down in terms of sine and cosine term. So therefore sine and cosine, they are oscillator function and sinusoidal function, hence it's periodic over space and time. Or sometimes you can write in terms of cosine function is, you may require in a complex form, which is a e to the power I k dot r minus omega t plus phi. As I said, in principle, you can derive this as we have done for a harmonic oscillator case. But as I have been saying you, whenever you are using any symbol or notation, you have to mention explicitly. Otherwise, they don't make any sense. So here, the psi RT wave function of the wave. What is wave function? Wave function carries all the information, and we can get, amplitude, time period, energy from this wave function. Like from displacement, we can get velocity, acceleration, energy. Similarly, at the wave function, you can get whatever the physical measurable quantities. As I said, amplitude, frequency, energy, and so on. And here is the amplitude, omega 2 pi f angular frequency, and this capital K is the wave vector, and the magnitude of the wave vector is now wave number, which is 2 pi over lambda. And what is K cap? K cap, as I said, the propagation vector and then wave number, and this will be your unit wave vector. And phi is the phase associated with the wave. And R, as I said, the R vector is the position vector, and I can write I cap K X, J cap Y, and M cap Z, where I cap, J cap, and M cap are unit vectors along X axis, Y axis, and Z axis respectively. Is it clear to everybody? Am I audible?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
So you might have seen these things, right? Wave number and wave vector, position vector, angular frequency, amplitude, right? In your 10+2 physics. Okay.
Yes, sir.
Yes, sir.
So now, as I said, you can derive in principle, right? I am not going to derive it. And as I said, you can derive it. So then this is the solution at a given position and time. But as you know, the wave function also varies periodically with position and time. And since it varies periodically, so therefore, when you say something vary over a variable, we normally talk about the derivatives. Changes means we should look at the derivatives in mathematical language. So therefore, since wave function varies periodically with both position and time, so the derivatives of the position and time must be associated with the wave equation, and that will explain the wave dynamics. Like the equation of motion in simple harmonic oscillator, which is d square x of t over dt square plus omega naught x of t equal to 0. So this is a differential equation, and that explains how the displacement changes over time or evolves over time. So similarly, the derivatives, like here, the second derivatives is associated with the position of the displacement. Similarly, the derivative with respect to position and time should be associated with a differential equation in order to explain the wave dynamics. And in principle, as I said, one can show that a second order partial differential equation requires to explain the wave dynamics. Therefore, wave equation would be like this. So you can derive it, right? In fact, you have to derive it. So del square psi xt over del x square equal to 1 over v square del square psi xt over del t square. You can see the derivatives are associated, and now it is partial differential equation rather than ordinary differential equation. Why? There are two independent variables, namely position and time. Okay. And in 3 dimension, how many independent variable will be there? There will be 4 independent variable. 3 for position, namely x, y, z, and then time. So in 3 dimension, we should have 4 independent variable, and then the wave equation will be like this. So what is this symbol stands for? That downward triangle, the square, this is known as Laplacian. Downward triangle square, or sometimes people represent upward triangle, that is Laplacian. That means the del square over del x square plus del square over del y square plus del square over del z square. Right? Since we are going from 1 dimension to 3 dimension, 3 coordinate, then 3 derivatives will be associated. Okay, then we'll have this. So this is wave equation in 3 dimension. So now if I ask you question, how many independent variables are associated in a 3-dimensional wave equation? Then immediately you can give answer. There are 4 independent variables. If I ask you question, how many independent variables are associated with a 1-dimensional wave equation? What would be your answer?
2 variables.
Two.
2 variable. Okay, so now you understand. So this explains the wave dynamics, and psi xt is the solution of this equation. In principle, in order to check, you have to substitute any one of this, in expression here, and then everybody please go to mute mode. Those who have not muted, please mute. Thank you. Okay, so now we understood, little bit about waves. What is waves, and what are the equations that are associated with wave, which explain the wave dynamics. So now light is a wave, and then the question is, so remember, so our focus is the phenomena produced by light. So now we come to know that light is a wave, and it will follow these equations. And then the question here is, what will happen, right, when traveling in a medium, or in general, if more than one wave is traveling in a given medium, and in particular more than one light wave is traveling, let's say in a medium, or without a medium, with a medium or without a medium, because light wave can travel without a medium. So then when more than one wave travel in a medium simultaneously, that means they must travel in the same time. It's not like one wave will travel and after 1 hour another wave will travel. So then when more than one wave will travel simultaneously in a given medium, in general or in particular more than one light wave will travel in with or without a medium, what will happen? One phenomenon will occur, and that phenomenon is known as superposition. Therefore, the superposition waves can occur when more than one wave travels simultaneously in a medium. So when this happen, what will happen? So hello, am I audible?
Yes, sir.
Yes,
Yes.
sir.
Okay, thank you. So then this phenomena is known as superposition. And the principle of superposition says that we know that psi xt represents the wave function, and deal with one-dimensional wave. Whatever result we will get for one dimension, we can extrapolate to 3 dimension. So the principle of superposition says that the resultant wave or superposed wave should be linear combination of the individual wave, or we can say component wave. That means if n number of waves are traveling simultaneously in a given medium in the same direction, then the superposition can occur. We'll have a final wave which is known as resultant or superposed wave, that will be like this: C1 psi1 plus C2 psi2 plus C3 psi3 and so on. What are the C1, C2, C3? These are the coefficient or that weightage, how individual will contribute to the resultant wave. And you can see it is a linear combination. C1 psi1 plus C2 psi2 plus C3 psi3 and so on. It is not non-linear combination. When you will have a non-linear combination, your higher term will come. For example, psi1 square, psi2 square, psi3 square, or psi1 psi2, or psi1 psi2 square, and so on. But since these higher order terms are absent, these are called the linear combination. So do remember, the solution must be a linear combination. that we have already seen in harmonic oscillator case. Whenever we have two solutions, we make the linear combination like a x1 a1 x1 plus a2 x2 like this. Okay, and then and to make the problem further simpler, we should deal with two waves. Okay, and then we should consider that the wave number and frequency of these two waves are same. The only things are different are their amplitude and the phases. Be much simpler. Okay, so because we are aiming to explain the phenomena produced by light, where the most of cases the amplitude of the light wave they differ or varies, as well as there will be phase factor associated with the both waves. So in that spirit, so what will happen, we consider that two waves with same frequency and wavelength, in other words the same wave number and same angular frequency but different amplitude and phase they travel in a medium, and therefore superposition can occur. Is it clear so far, everybody?
Yes, sir.
Yes.
Yes, sir.
So now this is only mathematics. You have psi1 plus psi2, and since the coefficient here a1 a2 is stand here, so therefore a1 a2 is appearing here. Or you can use c1 psi1 c2 psi2. Okay, so these are in factor. You can write down in another constant. It does not make matter. So assuming that c1 and c2 is 1, so therefore both waves are contributing equally to the resultant wave. So therefore we have this equation. And if you simplified it, that I have done here, what we'll get that this form. Okay, please check it. And finally we have this a sine kx minus omega t plus phi. What is a? Amplitude of the superposed wave. What is phi? Phase associated with the superposed wave. And this is a in terms of the amplitude and phases of the component or individual waves as represent equation 1. What is delta phi? It is the difference between component wave phase factor phi 1 minus phi 2. What is phi? Which phase associated with the superposed wave? It is tan inverse a1 psi phi 1 plus a2 sin phi 2 divided by a1 cosine phi 1 a2 cos phi 2. Okay, so now what we come to know that the superposed wave amplitude A and phase phi, they too depend on the amplitude of the component waves as well as the phases of the component waves. So now whether this amplitude A, whether it will be maximum or minimum, that does depend on the phase difference between component waves delta phi. For example, if delta phi is pi by 2, this term will be 0. It will be simply square root of a1 square plus a2 square. When delta phi equal to pi, okay, so this will be minus 2 a1 a2. When it will be 0 or 2 pi, then it will be plus sign. So depending on the phases delta phi, the amplitude A could be minimum or maximum. So that I have written down here. So when this delta phi is constant over time, it varies between minimum and maximum, and that is known as coherent superposition. And when this is not constant over time, say changes randomly, the amplitude A will be remain constant, then it is known as incoherent superposition. Got it? So let me move quickly. So whatever we said here, let's analyze it. So in coherent superposition, delta phi is constant. When delta phi is constant, and then as I said, it could be maximum when delta phi equal to 2n pi, because cos of delta phi will be plus 1, then it will be maximum. So only mathematics, right? And it will be minimum when delta phi is 2n plus 1 pi. As I said, when delta phi equal to pi, 3 pi, and so on. So this will be this. So now it will be minimum or maximum if delta phi remains constant, whether 0, pi, this thing, it is a constant. So when delta phi remain constant in one of the values, either it could be a minimum or a maximum. And similarly, hello, do you able to hear me?
Yes,
Yes,
sir.
Yes,
sir.
sir.
And similarly, as we know, the intensity is directly proportional to the amplitude square, and the maximum intensity will be this, and the minimum intensity will be this. Because in light, we looked at the intensity, not amplitude, right? We measure intensity or therefore the power. So now we got to know that when delta phi is a constant, it could be either maximum intensity or a minimum intensity or in between this minimum and maximum depending on the delta phi values. So and if I1 equal to I2, the intensity, which is I0, what does it mean? That waves coming from a common source. When both waves are coming from common source, they might have, different phases, but they will be same amplitude because it is coming from common source, so therefore same intensity. So this case, the maximum will be 4I0, and what will be the minimum? Minimum will be 0. That means when two waves are coming from a common source, that case, the intensity will vary minimum to maximum 0 to 4I0, depending on the relative phase delta phi. And therefore, since it is coherent superposition, and the waves associated with such kind of phenomena is known as coherent waves. So that I have written down here. Therefore, the coherent superposition of two waves, say light beams from a common source, that means the intensity of the first and second wave are equal, which is I0, leads to distribution of intensities within minimum to maximum. And this phenomena produced by light in the context of light wave is known as interference. And the light beams or waves associated with the interference, which is, example of coherent superposition, are known as coherent sources of light. And the classic example of coherent source of light is laser light. Laser is an abbreviation or acronym. It stands for light amplification by stimulated emission of radiation. If you, combine the first letter of each word, it will L-A-S-E-R, laser. So in short, what we understand here that when there will be coherent context of light wave, then we call it interference. And the light waves associated with the phenomena of interference is known as coherent sources of light. And when interference occur, the intensity of the resultant wave, it distributes between minimum, which is 0, and maximum, which is 4I0. If two coherent sources of light are associated with the interference. So now, am I audible?
Yes,
Yes,
sir.
sir.
Yes, sir. Yes,
Yes,
sir.
sir.
Okay, so let's talk about incoherent superposition. Delta phi is constant. Constant. It means changes randomly over time. When delta phi is random, when we have a random event, what we would like to know, how we'll measure it? We should look at the average value. Okay. So for example, you toss a coin many times and you record heads or tails and you take the average value. Okay. So similarly, since delta phi is random, since it is random, therefore it is not constant over time, you should look at time average. And what is the average value of cos function? What is the average value of cosine function?
0.
0.
0.
Okay. So therefore the average value of cos delta t over time is 0. To remember this delta phi, it does depend on time. It is time dependent. Okay. So the average value of cos delta over time is 0. So since it is 0, it will be simply square root of a1 square root. So it is a constant. And similar, the intensity will be I1 plus I2. And if I1, I2 equal to I naught, so it means light waves from different sources with same intensity. Okay. So light waves from different sources with same intensity. In that case, you can have, the phases associated with the individual source of light, they can vary randomly. So therefore, the delta phi is not constant. So therefore, I say different sources intensity. But in coherent superposition, same sources. But here, different sources with same intensity. So I naught, therefore the resultant intensity will be 2 I naught, which is a constant. So therefore, the incoherent superposition of two beams applied from different sources leads to uniform or constant distribution of intensity. The light beams or waves associated with incoherent superposition are known as incoherent sources of light. And what are the classic examples? So these are, examples light that we observe or receive from the common source like sun, stars, electric bulb, candle, etc. These are, well-known example of incoherent sources of light. So, and here is the, the intensity distribution diagram. When you have coherent superposition, so assuming two waves are associated, so it varies maximum 4 I naught to minimum 0, whereas for incoherent superposition, it remains constant, which is 2 I naught. So now we come to know when there will be coherent superposition, the intensity will distributed between minimum to maximum, whereas in incoherent superposition, the intensity will remain constant. So if I ask question, if there are three waves are associated in superposition, and if it's a coherent superposition, what would be the maximum intensity? Anybody? Do you able to hear me? Am I audible?
Sir, please repeat the question.
So assuming three waves are associated in the process of superposition, and if it's a coherent superposition, and the intensity of all these three waves are same, let's say I naught, what would be the maximum intensity if coherent superposition occur?
3 I naught.
9 I naught.
Yes, very good, 9 I naught. And what is the minimum intensity?
6 I naught.
0. When you have a coherent superposition, do remember it does depend on this, right? If you have coherent superposition, n square I naught will be maximum, 0 will be minimum. If you 2, 4 I naught, 3, 9 I naught. And if it's a 4, 16 I naught. And if it's an incoherent superposition, it's simply n I naught. Got it? So this is for incoherent and this is for coherent. So this is all about coherent and incoherent superposition, and at the end what we come to know, the interference. The coherent superposition in the context of light wave is known as interference. And in the next class we'll be discussing about interference. Okay. So any question or doubt on today's lecture?
No, sir.
By the way, so I am going to share the lecture notes as well as today's recorded lecture, and if you have any doubts you can go through them. Okay.
Yes, sir. Hello.
Yes. Yeah, tell me.
Sir, in assignment question number 21 and 22 are same.
Is it?
Yes, means
Okay.
they are talking about deriving energy expression.
Okay, then you work any one of them, okay? If they are
Okay,
same.
sir.
Any question or doubt? The discussion, right? So doubt clearing means what? I mean, is it on assignments or overall? Could you please unmute and speak to us? Assignment. So assignment yesterday I had already told you, right? So even if you worked out a couple of problems and okay, it's okay. Yeah, but I can see your chat. So let me clarify. So you are free to discuss among yourselves. For example, yesterday somebody asked questions and we did discuss, right, how to solve this problem. I think some problem number 12 or maybe 9, something like that. So you are free to discuss among yourself, and if you have any difficulties or doubt, then we can have discussion section. So how many of you have done successfully all these assignment problems? Yes. So Rishikesh has done, right? So he can have you done all the problems?
Yes, sir.
Yes, good. So now at least one of from your group he has done, and you can do, and you can discuss with him also. Okay. And anybody else except Rishikesh? You try to solve it, okay? And if it's you find difficulties and real need to discuss, then we'll have an extra class to discuss about assignment problems. Is it clear to everybody? Today, in fact,
Yes, sir.
I taught a lot, but I hope you got the message what I was trying to convince you. And you please go to my channel if it request a video lecture and revise yourself. And in the next class, so tomorrow, so so tomorrow we might not have a class, right? Because of what is that? Some Pongal, right?
Sankrant.
In the south side we call in Pongal, and here is Makar Sankranti, and so therefore tomorrow should be a holiday, official holiday, right? Yes or no?
Yes, sir.
Yes, sir.
So tomorrow might
Yes.
be an official holiday. So tomorrow, if it's official holiday, we will not conduct class. I'll check and let you know over WhatsApp. It's not official holiday. We'll have a class. I think it is an official holiday, and let me check. I'll also communicate over WhatsApp. Okay. So bye.
Yes,
We'll
sir.
meet in the next class.
Thank you,
Bye,
sir.
Thank you,
everybody.
sir.
Thank you.
Thank you, sir.
Okay, sir.
Thank you, sir. Thank you, sir.
Thank you,
Thank you,
sir.
sir.